All right, so is this working? Okay. So the second talk of the bootcamp will be property testing of Boolean functions, and it'll be given by Erik Waingarten. And
Thanks.
let's go.
Okay. First, let me thank the organizers for inviting me. It's really great to be back in Berkeley. And this talk, so I was asked to give a bootcamp talk on property testing of Boolean functions. It's supposed to be an introduction, but let me tell you about my main goals. So my main goals for this talk is just to go through definitions and do as best as possible to try to motivate the reasons why we've defined things in certain ways, as well as cover very few but very important ideas in property testing. So I'm gonna take the opportunity to tell you about linearity testing, and that's gonna be most of the talk, and it'll help me introduce some of the notions and some of like the key ideas. And we'll briefly talk about monotonicity and juntas. And I just wanted to point out these two references. I'm getting some feedback there. Introduction to Property Testing, this book by Odette Goldreich, as well as this survey by Dan Aron. I didn't know about the new textbook, but I'll also check it out soon. Okay, so the talk is about testing Boolean functions. And for the most part, we're going to be talking about Boolean functions whose domain is the Boolean hypercube. Okay? So what's a Boolean function? It's a function that maps to 0 or 1. Okay, so it encodes some subset, some set of its domain. So the whole game for this talk, we're dealing with these kind of functions that take as input n-bit strings and output either 0 or 1. And I'm going to represent the domain, the Boolean hypercube, in 3 different ways, and they're going to come up in the various different contexts. So let me just walk you through these pictures. So here on the left, I'm drawing a 4-dimensional hypercube. And you should really think of the bit vectors as corresponding to the vertices of this cube, and then these lines are the directions, or corresponding to the different coordinates. And as we'll see, it's sometimes useful to take this cube and view it as a partial order. So you could take, say, the vertex that corresponds to the all 0 string, you push it down to the bottom. You take the vertex that corresponds to the all 1 string, you pull it out to the top. You end up with this diagram where effectively, as you move up this diagram, this corresponds to flipping bits from 0 to 1. And the width of this is supposed to represent the rough approximation of how many vertices are at a particular level of the cube. And then finally, this picture is just meant to represent a Boolean function as a computational device. So where you'll have the input is going to be written here, and you'll read the input in a particular way, and then that will output the bit 0, 1. So these pictures will come up. OK. So what I'm going to do is, a property testing algorithm, it's an algorithm that decides whether a function has a particular property approximately. Okay, so I'm just going to describe the basic setup. There's going to be a player Alice, and Alice has access to some Boolean function, but she doesn't get to see the Boolean function. She can only query it. So there's this dotted line to represent that the function kind of lives in a Alice doesn't get to see it, and she's interested in whether the function has a particular property. So the game is that an algorithm, or what Alice has to do, is she makes queries to this function. So she submits what's the function value at x1, and maybe gets the value f of x1, what's the value x2, and so forth to xq. Q is going to be the number of queries that Alice makes. And based on the query values that Alice has made, she needs to decide to output yes or no. The decision of does she believe the function has a property, or no, she believes the function does not have a property. So here's like some picture. Maybe this is the set that the Boolean function is representing. This corresponds to the queries that Alice makes, and that's when she comes up with an answer. So I want to take maybe the next slide just to motivate what are we going to mean when we talk about approximately. This is something maybe a copy of what Arthur talked about in the last talk, but specialized to this world of functions. So let's just go through this very brief, simple example. Alice wants to determine, is my function always 0? Okay, is it just the constant 0 function? And the key here is there's a very natural algorithm. In a way, Alice should try to check consistency with the fact that the function is always 0. So she'll sample some random queries. She'll ask for the function values at these queries. And if she ever sees a function evaluation of 1, well, she knows for a fact that the function is definitely not the all zeros function and can reject. But otherwise, she'll say, well, I've seen all zeros. I'm in a scenario where it's consistent with it being all zeros. And she'll say the function is always 0. And the reason why approximation comes up is because, well, unbeknownst to Alice, we could have been in a world where the function really was all zeros except for one point. Okay, maybe this gray point that I added. And really, unless Alice queries that hidden point that evaluates to 1 that she didn't know about, the view that she observes, it looks like the constant 0 function, even though this function f tilde is not the constant 0 function. Okay, so this motivates the notion of approximation. We can't hope to be able to exactly determine whether a function is all zeros or there's a single one unless the query complexity is essentially such that she is very likely to find this hidden point. And that requires 2 to the n queries. So this really motivates the main definition of property testing as some form of approximate decision making. So what's the definition? So a property testing algorithm for a property P, think of this as the functions that you're interested in. In the previous case, it was the constant 0 function. It's a randomized algorithm which receives query access to some unknown function. And the guarantee, or what you want from the algorithm, is that it satisfies this approximate condition of determining whether it has a property. So if the function does have the property, or the function lies in the set of functions which have the property, then the algorithm should output yes with probability at least 2/3. And if the function is what's called epsilon far from having the property, the algorithm should output no with probability at least 2/3. Okay? So I'm going to talk about exactly what I mean by epsilon far. But the picture here is I'm thinking about this rectangle as the space of all possible Boolean functions on the hypercube. Among those, there's a set of functions which have my property. That's this innermost oval. And that means there's a natural question of trying to determine whether the function lies inside this set or outside the set. And what I do is I define some measure of distance or some measure of closeness in the space of functions so that I can talk about a function being in my property. That means it lies in the set, or it's somewhat far from having the property with respect to that metric inside the space of functions. So maybe that's one way to think about it. And when you come up with proofs of an algorithm being a property tester, this is usually the definition that I'd like to think about. But there's a perhaps equivalent, but sometimes more illuminating definition if you take the contrapositive of the second statement. Right? So what does it mean? You want an algorithm such that if your function has the property, the algorithm should certify that indeed you had the property with probability at least 2/3. And furthermore, if you run your algorithm and the algorithm says that you have the property, then it better be the case that, well, if you didn't have the property, it was because of some minor case, like there was some hidden point that you needed to query. Okay, sometimes this is more useful of you run, instead of epsilon farness, you're saying, I have an algorithm, and in the case the algorithm outputs, yes, it has a property, then some good things happen for my function. Okay. And for this talk, and for Boolean functions, usually the notion of epsilon farness, or this metric on the space of functions, is just given by the probability that two functions differ on a randomly sampled input. Okay, so when I say that f is epsilon far from the property, or that the distance between the function and the property is less than epsilon or more than epsilon, then this means that the closest function g, the minimum of the probability that they differ, is at least epsilon far from, or they differ on at least an epsilon fraction of the inputs. Okay, so this is saying that if your algorithm outputs yes, with some certain high probability, it must be that there was actually a function that did have the property that was fairly close. Okay, so then going back to kind of the tester for the constant zero function, the formal analysis just proceeds by, well, let's fix this algorithm that samples q points uniformly at random, queries all inputs, and it outputs yes if and only if all the function values are 0. In my picture now, this property p consists of a single function, the all zeros function. And this gives me like an epsilon ball, or all the functions outside of the circle correspond to all functions for which there's at least an epsilon fraction of the domain whose value is 1. So this is epsilon far from having the property. So in the first direction, if the function actually belongs to the property, then it's always 0. So the algorithm definitely outputs except. And if the algorithm does output except, then it must mean that the probability that the function values equals all 0, well, it's going to be at most a probability that you avoided any one string. So this would be 1 minus the fraction of the values that are equal to 1 raised to the power q. And if your function was epsilon far from having the property, the fraction of 1s is at least epsilon. So you need to set q to be roughly 1 over epsilon before this probability becomes very small, less than 1/3. I want to mention just two minor points about this algorithm. It has some additional properties, which I'll say that it's a non-adaptive algorithm in the sense that all the queries were done in advance. And even though at the beginning, when I displayed property testing as this game, there was a natural x2, the second query may have depended on the first query. Actually, all these queries are completely independent, and the algorithm itself could have been done in parallel. And in addition, it has this notion of one-sided error, which means that if your function lies in the property, then you always say yes. And alternatively, this means that if you say no, then it's because you have a certificate, you have a proof that the function must not be in your property. Okay. Just a very minor observation that the thing that we had done before is actually more general than just for the constant zero function. And basically, the same exact proof shows that one can always test properties of very few functions. So the observation is that for any property p, there exists an algorithm that tests for that property with query complexity, which is logarithmic in the size of the property divided by epsilon. Right? The whole point is that we use log p, many more queries, to test whether you're exactly each function in the property. And this additional log factor allows you to union bound over all properties. OK, so that's going to be it's a generic tester. Whenever you have a property, you can test with a number of queries proportional to log of the size of that property. But this can be quite bad, right? Because the number of functions is, well, the ways to fill out 2 to the n points. So that's 2 to the 2 to the n. This would give you a 2 to the n factor here. But this algorithm itself is actually much more powerful. It actually tells you which is a function in your property that would be close. So it actually learns a function in the property p. But at the same time, it's completely generic. Okay, so if your property is small enough, you could hope to do this. In general, this is quite bad. OK, so now I'll tell you maybe I think it's one of like the first really awesome results in property testing of Boolean functions. This question of, is my function linear? Okay, so I'm going to talk about this paper of Bloom, Luby, Rubenfeld in '93. Where they were considering the property of the function, the Boolean function, being linear over f2. Okay, so let me tell you the definition. A function f is linear over f2 if you can represent f as a linear function with respect to each of the coordinates. Oh, you didn't do f2. OK, never mind then. OK, well, I'll talk about f2. OK, good. So, but this is a natural definition. So yeah, so the AIs are itself a bit string in 0, 1 to the n. It tells me in a sense, which of the coordinates, if a coordinate I is set to 1 in A, it tells me, well, you better pay attention to that coordinate. And the function simply sums up those coordinates and considers whether they're even or odd. So if A was all zeros, then you're not looking at anything. I mean, the function is always 0. If A is 1, so here I'm drawing maybe this is the fourth, this direction corresponds to the fourth coordinate. This function is the function that only looks at whether the last coordinate is 0 or 1. So it's a dictator with respect to this final coordinate. That's why all these quantities are set to 1. And finally, when you look at all the coordinates, this is the parity function. It's kind of hard to see from this picture, but if I show you the other diagram, whenever you're at a point and you flip something, well, that's going to flip the answer. This is the parity function. OK. So that's a property that we're going to consider. And yeah, basically, we can go through what are the property testing algorithms that essentially what is the naive benchmark that we've seen, and then what is a really awesome tester that I'm going to tell you about. OK. So the naive benchmark is just to consider, well, this property of linear functions is not too big. Right? The number of linear functions is 2 to the n, corresponding to all the possible values of A. So by the observation that we had before, there is a natural tester whose query complexity is log of the size, so that would correspond to n over epsilon. Okay. Actually, you can do slightly better with the same idea by first trying to learn what this vector A is, and then testing consistency against the vector that you learned. Right, so here's a slight improvement to a query complexity of n plus 1 over epsilon instead of n over epsilon, which basically says, well, first, I'm going to query an estimate of AI. Right, how should I query AI? Just if you query EI, which is the vector which only has one non-zero entry at the ith entry, that would essentially, if my function was a linear function, that would allow me to read off what is the corresponding value of AI. So I make those n queries, and I come up with a learn, essentially, if the function is in fact linear, it would be this linear function. Yeah. And then I just check consistency against that function. OK, this gives me the slight improvement. OK, but we're really going to the whole point of, or a big theme in property testing is that you can oftentimes design much more efficient algorithms that don't need to actually learn the function. So you run an algorithm, and even though you can't point to a specific reason why you're in the property, you nevertheless can conclude that there must be a function. You must be in the property, or there must be a function that's very close to the one that you've been querying. Yeah.
Question. Would something like this work in this space instead of having P, you pick an epsilon net for P and then checking whether you are close to one of those points? Is such a definition meaningful?
Sorry, what do you mean?
Like for P, for instance, can one define a meaningful epsilon net, which hopefully will be much less than 2 to the n?
Yes, if you had, yeah, good. So if you had a better way to discretize P and still be saying that, well, your function is close enough, then yeah, you could improve on this by taking a net of P. Yeah.
But such a thing exists, for instance, for this linear?
For the linear functions, I think it's going to be difficult, and the reason is that these functions themselves are pretty far from each other. Okay. So now let me give you a different definition of what it means for a function to be linear. And that itself is going to lead to a natural test, which is really the main, I think, well, now I'm second doubting whether it was the main result in BLR or not. But OK, so what's the definition? So here's an alternate equivalent definition for what it means for a function to be linear. So function f is linear if for any 2 points in the domain, if you query f of x and f of y, this is always going to be equal to f of x plus y. This is taken in f2. So you can check that, in fact, these definitions are equivalent. So if you do satisfy for every x and y your function is linear, then there's a consistent a that would explain why all these function values are the way they are. And this itself leads to a natural algorithm that checks the consistency of that definition. And the whole goal is to analyze to what extent does this algorithm give you a good property testing algorithm. Okay, so what's the algorithm? Well, we're just going to check whether this definition holds, but we can only check it on randomly selected inputs. Right, so the goal is to sample pairs, xi and yi, and I'm going to query and check whether f of xi plus f of yi equals f of xi plus yi. So for each I, I'm paying 3 queries, and I'm going to repeat essentially q times. And if you are a linear function, it should be the case that all the things that you've sampled do satisfy this consistency check. So if they do, then you output yes. Okay? Otherwise, if you spot evidence of nonlinearity, then you output no. Okay. And maybe just like as a quick aside, I think the whole point of, there's a certain sense in which this definition is nice for property testing, because it's a certain local definition that you can just check 3 inputs in order to determine whether the function is linear or not. And the main point is that even though a low query algorithm cannot check this for all quantification, you could hope to analyze, well, can you derive this closeness to being linear by this probabilistic guarantee of just this algorithm succeeding with certain high probability? Okay, so now whenever I learn of a new algorithm, sometimes in order to appreciate kind of how awesome this is, you need to go through, okay, what could have gone wrong, and what are the main challenges that were involved in proving that actually this test actually works, and why am I saying that this is so cool? So I'm going to go through 2 potential bad cases, and hopefully I want to convince you that these things could have actually happened, but the fact that they don't happen for this test is itself surprising. So the first bad case is that you're going to query some function, and now it could be the case that the function itself is not linear, but it's not linear because there's portions of that function that are linear for different reasons. And I'll show a picture. I'll say what I mean by that. And the second bad case could have been that even though the function that you'd be querying is far, the evidence that it's nonlinear may be hard to find. Okay, maybe that there's only very few of these pairs which violate this property. Nevertheless, if you actually wanted to fix everything, you would have to make a lot of changes. And I'll give an example of that too. Okay, so what is the bad case 1? So imagine my function that I'm trying to analyze. It's a function which is epsilon far from being linear. This means that there's no one consistent linear function that agrees on everything. And furthermore, the closest one differs on a lot of inputs. But the reason that this is the case is because actually the function can be divided into like these 4 portions. Inside each portion, there's a completely consistent linear function. But these vectors, a1, a2, a3, a4, are actually different. And this would mean that there's no global linear function that aligns with everything. Yeah?
Why is this a bad thing if this happens?
So this function, even though the portions of the function are not linear, are linear, the function itself is not linear because you can't reconcile these values. Yeah, exactly. So I'm going through. So this algorithm will work. I'm just.
So if I pick 2 random points that will go to 2 different parts.
Yeah, exactly. So I mean, the algorithm does work. I'm just to like to specify, like the bad thing that could happen is that had you designed an algorithm in a different way, such that instead of querying randomly chosen points, you would have chosen 3 points, but these 3 points happen to fall in the same region, maybe because you were querying 3 nearby points. Then this could have been a problem, because if you ran the test on each individual region, you would individually see that they behave linearly, but it really was because you didn't jump across portions. Okay, but like I said, the test actually does work. So we'll see that, in fact, because you sampled it linearly, you kind of have to jump through the various portions. And if you're seeing a consistent answer, it must be the same consistent answer throughout. So, OK, in order to go through case 2, I'm going to define a different definition of linearity. This could have given, this is also a definition of linearity. It would have given rise to another natural algorithm. Nevertheless, that algorithm doesn't work because it's going to be hard to find the other type of evidence. OK, so let me give you another definition of linearity that says a function f is linear if now you're only going to check the condition against the n directions that define A. Okay, so if x plus ei equals f of x plus f of ei. Okay, this is also a definition of linear function, but it's going to turn out that had you used this definition, you would have come up with this test, which would have sampled x, would have sampled I, and would have checked this condition. But this algorithm doesn't quite work in the same way that the BLR algorithm. And the example is just the following. Consider the function which is the majority function. Okay? So if the number of 1s is less than n over 2, it evaluates to 0. If the number of 1s is greater than n over 2, it evaluates to 1. Now this function is also far from being linear. But if you run this test on just a few examples, you're not going to spot the evidence of nonlinearity. And the reason is when you run this test, in order to find the evidence that the function is nonlinear, you're going to query ei. So all your ei's live down here and always evaluate to 0, which means that the test only fails when f of x is not equal to f of x plus ei. And this only happens for a tiny fraction of the cube. Only if you had queried an x, which was exactly n over 2 1s, would you be in the situation that f of x evaluates to 0, but when you flip the ith bit, that evaluates to 1. If f of x had a lot of 1s, then adding 1 or subtracting 1 wouldn't have changed anything, and similarly for the all zeros. Okay, so this is also another natural definition of linearity. Nevertheless, this requires square root n many queries in order to test. You basically have to sample an x in this boundary. OK, so let me go through just the high-level idea in this theorem of BLR that shows that this test, actually just 1 over epsilon, many repetitions suffice. In a sense, you can also think about this along the lines of it's a test so efficient that you won't be able to identify a fixed setting of A, which would make your function linear. Nevertheless, you can conclude that such a setting of A exists if your test passes with high probability. And in some sense, in a lot of these works on property testing of Boolean functions, the main difficulty and the main challenge is that if you start out with a function that's epsilon far, you want to try to get your hands on some function in the property so that you can do your analysis tailored to that function. So the game in BLR is, well, what is this function g going to be? And I'm going to base my analysis of my test in terms of how f and g differ. So toward that end, the paper defines this, this notion of a voting function. Okay? So what is a voting function? So it's going to be my function g. And it's essentially going to say, for a g of x, what should the setting of x be in f such that my test would pass? Okay, so in a way, imagine you had fixed the x in your test. Then, in order for you to pass, it must be the case that when you sample a random y, f of x plus y should be equal to f of x plus f of y. So in some sense, you're considering for each y wants to set what should the setting of x be such that for this query between x and y, my test would pass. Okay, so the voting function basically says, what should it be such that the test pass with probability at least a half? And then the proof of this test really proceeds by two important lemmas. The first lemma is you should interpret it as saying, look, if your function f of x disagrees with what x should be in order for the test to pass, then you're in a pretty good case. This means that the battle is almost won. You've sampled a point, and that point would like that it should be set to some value such that the test passes often. However, the function had set it to a different value, which essentially means that if you sample a random value, you will find that evidence of nonlinearity. Okay. The second lemma actually says, well, this function g that I just defined seemingly arbitrarily is actually linear if the test passes with some high probability. Okay. So these are the two important lemmas. The crux of the argument, I'll just go through how you would apply these two lemmas. You start and you say, OK, imagine you're holding onto a function which avoids catching mistakes often. Then by lemma 2, we know that if my algorithm oftentimes passes, the function that I define g has to be linear. So the function of g is linear. So the assumption is that if you're epsilon far from being linear, then the distance between f of g has to be at least epsilon. But then we apply lemma 1. And we say, well, if f and g disagree on an epsilon fraction of the inputs, with probability epsilon over x, you will find an x where f and g disagree. So the battle is almost won. And then when you sample y, you will catch that mistake. OK. And really, the whole game is the proof of lemma 2. This is the non-trivial part of the paper. But what perhaps surprisingly that they show, and I'm not going to go into the details here, is that actually I could have defined this function g in a much more strengthened way. So here I defined it with respect to 1/2, 1/2, because among all the inputs, each input either wants it to be 0 or wants it to be 1. Actually, I might as well have defined it as an overwhelming majority of the inputs are voting toward x being set to 0 of x being set to 1. Okay, this itself is a non-trivial statement. But once you have this, it's not that hard to show that the function g is in fact linear.
But that's not well defined, right?
It's not. So it is well defined if the test often passes. Yeah. So the whole game is how do you connect the probability of success of this algorithm to the fact that this function must have been inside the property. OK, so that's all I wanted to say about linearity testing. Just give you like a basic overview of some of the ideas involved and how to get into a function that's linear and analyzing the success of your test in order to analyze this closest linear function. And I just wanted to go through a quick digest of the important ideas. First, we talked about definition of approximation in property testing and why it was really necessary. We saw this generic log p over epsilon query tester for any property via like a very naive type of learning. And then we saw the linearity definition and the fact that, well, not all algorithms could have succeeded equally as well. There was a better algorithm via learning that made n plus 1 over epsilon many queries. The fact that, well, if the bad case, had we defined linearity in a different way, that would have led to a test which wasn't good. And then this process of getting a linear function via this voting, which is known in the literature as self-correction. The way the function itself, because you went from, yeah, anyways, let me not say so much. I will say that there's a different proof of the linearity test, but proceeds by some Fourier analytic techniques. It's a paper of Belair, Cooper-Smith, Hastad, Kiwi, and Sudan. But I learned about it from Ryan O'Donnell's book, The Analysis of Boolean Functions. So that's another very slick proof, but maybe not as intuitive or maybe not as algorithmic as this self-correcting approach. OK, cool. So now I'm going to move on, or I guess if there's any questions on the previous part, I'm happy to take them now. Okay, great. Okay, so then the second property that has been very intensely studied and there's been a lot of recent progress on is the question, is the function that you're holding on to, is it a monotone function? So what's the definition? A function f is monotone if and only if f of x is less than f of y for any value x, which is less than or equal to y with respect to the partial order. So here's where this picture of this diagram comes in handy. At the bottommost point, this is the all zeros string. That's the L1 string. Essentially, the height, as I move up in this diagram, I'm flipping bits from 0 to 1. So these represent my partial order in the space. A monotone function is a function for which, as I walk up this diagram, I only go from 0 to 1. Okay, I can't go back from 1 to 0. So some basic examples are, well, if f of x equals just xi, it looks only at the ith bit. This function is monotone, right? Because if xi is 0, it values to 0. As you walk up, eventually you're going to flip I to 0. That's the moment the function will flip to 1. Right, from 0 to 1, that's the moment it'll flip to 1. But it will never flip back. The second is the majority function, the function that we already saw, where in the bottom half is set to 0 and the top half is set to 1. Also, from the picture, you can see as you walk up, you can only go from 0 to 1. What's an example of a function that's not monotone? So imagine I had the function as before, but I've put in some points here that all evaluate to 1. And this function is not monotone because if you query, say, at the point x here, well, eventually you're going to step out and evaluate to 0, and that will be a violation of the assumption that your function is monotone. Okay. The definition of monotonicity clear? Okay, this is a natural, like a Boolean version of monotonicity, where the input domain is this partial order on the Boolean hypercube. Okay, so let's just briefly go through the natural tests, or the tests that come from the basic definitions of property testing. So on the one hand, you can take the generic test and just count how many monotone Boolean functions are there. This number is actually called the Dedekind number. I learned that while making these slides. This test is actually really bad because the number of monotone Boolean functions is actually quite large. So even if you take the log, you still end up paying n choose n over 2. Okay, this is exponential in n over 2. It's exponential in n over, yeah, there's a small order improvement over 2 to the n, but it's very bad. There's a non-trivial learning algorithm. So there's an algorithm of Bashudi and Tamon in '96 who showed that, well, if you are given queries to a Boolean function and you want to learn a function that's close enough, you can do this with 2 to the root n over epsilon many queries. So this is non-trivial, much smaller than this. And in the same way that the non-trivial learning algorithm for linearity gave us a minor improvement, you could use this learning algorithm and then check consistency against what you learned and get a 2 to the root n query algorithm for testing monotonicity. Okay. But similarly, you can also define another definition for what it means for a function to be monotone. This definition is equally good as the definition I had on the previous slide, but this definition leads to a natural test. And the original paper, which of Goldreich, Goldwasser, Limenron, and Samrodnitsky, they show that actually this test will give you an efficient tester for monotonicity. Okay. So what is the definition? Well, a function f is monotone if and only if, well, it just suffices to check my condition of monotonicity on 2 strings, x, where the ith bit is set to 0, and x, where the ith bit is set to 1. Okay? for any x and y. So this is just saying, well, before the definition was that for any pair of inputs, x and y, where x lies below y, then the value can only go from 0 to 1. It just suffices to actually take two inputs which differ on a single bit. And the reason this is equivalent, I mean, as you walk up, you can never flip from 1 to 0. And this gives rise to a natural tester. For testing monotonicity, you sample x, you sample I, and you just query both endpoints. You try to check the consistency of this definition. If you ever catch an input where f of x with I being set to 0, that evaluates to 1. But after you flip the ith bit to 1, the function value becomes 0, the function went down. That gives you a proof that the function is not monotone, and you can reject. Otherwise, if you always pass this test, then you always output accept. Okay. So here, in this function, whenever you query two pairs of inputs, x and x after flipping the ith bit, you will, if it's monotone, you will never reject. Right? So this is also a one-sided tester. The goal is that if you have a function that is epsilon far from monotone and has this region where flipping from 1 to 0 may happen, that this test will eventually catch that flip from 1 to 0. Okay, and then you would be able to say reject. Okay. And the main theorem here is that it turns out that n over epsilon many iterations of this edge tester suffice. And if you actually do run n over epsilon many such tests, and you never spot a violation to monotonicity, then this gives you this probabilistic certificate that there has to be a close monotone function. Okay. The structure of the proof of Goldreich-Goldwasser, Liman-Ronson-Rudnitsky, it has some resemblance to this idea of getting your hands on a close monotone function. And in some sense, they prove a structural theorem that says that if your function is far from monotone, there has to be sufficiently structured evidence in the form of these edges which witness that your function is not monotone. Okay, so there's going to be many such pairs, x and I, such that that flip is going to catch your non-monotonicity. And the way that they do it is by actually also defining an algorithm that takes your arbitrary function and finds a close-by monotone function. Okay, this is this transformation. It's different from this voting rule that we saw before. But nevertheless, their proof is by showing that analyzing the difference between f and g, it gives you a handle on how many such edges there could have been violation to monotonicity. I'm not going into as much detail as I did before. I just wanted to give the basic gist of the argument.
Did you say the definition of G? What was that?
Oh, so so what is this definition? It's a transformation that takes a function f, and it's going to output some function which is monotone. The transformation works by fixing each coordinate one at a time. So what is the transformation? At the beginning, you're going to fix the nth coordinate. So you're going to look at all the edges in direction n. And if you had seen a violation, you flip their inputs to remove that violation. The violation is a pair of bits, a pair of strings, which differ only on the nth bit. But when you did make that flip, your function went from 1 to 0. The transformation takes, whenever those occurrences occur, it just flips them. Okay. That turns out to fix the nth coordinate. And then they say, OK, let's apply that same fix to the n minus 1th coordinate. And then the n minus 2th coordinate. Now it's not clear that you didn't destroy your progress on the previous, but there's an argument to show that, in fact, you don't. So if you do this process, you get your hands on one function. And then you look, well, how much did I have to flip from f to g? This function is monotone, so the distance had to have been at least epsilon. And now you try to keep track. Well, what were the reasons why I incurred this distance epsilon? It must have been because some steps of this were flipping edges, and that gives me a lower bound on the number of edges which which were flipped from in F. And that gives me the structured evidence that I need for my test to succeed. Okay. There's yeah. N over epsilon. So yeah, I mean, there's some loss in analyzing the n steps, and the argument essentially each step may lose some factor. This means that there may not be. Yeah, I mean, the analysis of this test is in fact tight. So there, you do need n over epsilon for this test to succeed. Okay. In the past, I guess since 2013, Chakrabarty and Seshadri, they, I guess, took a different path for monotonicity testing, where they show a different structural theorem, and it gives rise to the analysis of a different test. So they show that actually not only do you have a lot of edges, there's a lot of very structured evidence of non-monotonicity. And they analyze what's called the path tester. Okay, so what's a path tester? It's, I guess for some interpretation, is the natural test that you would have come up with had you looked at the original definition of monotonicity testing. So what they're going to do is they're going to find a distribution to sample these pairs, x and y, where x is always below y, and just query those two. Okay? If the function is monotone, you expect the function value at x to always be less than or equal to the function value of y, and that's their test. They just repeat this test. It turns out, well, after a sequence of works, that if you only do root n over epsilon squared many such iterations, this suffices. And if your function was epsilon far from monotone, after these many steps, you're very likely to find such a violation. And I'll say that also this test is also naturally non-adaptive, and it also has one-sided error. So if your function is monotone, you always say that the function is monotone. Okay. So I wanted just to, I'm not going to go into detail about this. There's been a ton of work. And even over the past few years, there's still been a lot of progress. So I just wanted to give you a glimpse, cite a few papers on that. Yeah?
What is non-adaptive about this?
The non-adaptive comes from the fact that all these queries could have been done completely in parallel.
I was thinking you said adapt. It's okay.
No, sorry. Okay. So this test is non-adaptive.
Yeah, sure, of course.
So there's been a lot of work in trying to extend these ideas. And the proof of making this work is actually pretty complicated. And there's been, well, recent work by Black, Chakrabarty, and Seshadri extending these ideas not only to the 0, 1 hypercube, but the 0 to n, so larger domains. There's some query lower bounds. And then there's extensions to not only Boolean functions, but real valued functions. There's all been a lot of progress, and we still don't have the best algorithms or even the best lower bounds or vice versa for many of these questions. So this is actively being studied. Yeah.
Do we know the status of epsilon? So it's the correct number is the mean of n over epsilon and square root n over epsilon squared. But do we know what?
Yeah. So good. There are some regimes in which you can show some lower bounds. So for example, so this test is non-adaptive and also has one-sided error. If you insist on these conditions, I think this paper of Koopmans-Safra gives some evidence that actually this dichotomy where it switches is actually tight. But in general, at least these lower bounds, we've done them for constant epsilon. What is a distribution D? So the distribution D varies a little bit according to the various different papers. But roughly speaking, what they do is they sample X is just chosen uniformly at random. And then you try to guess how many steps you should take. Okay? And there's, maybe you guess by powers of 2. So first you guess 2 to the I for some random I many steps. and you flip those many random bits. So in some sense, you need to choose. The choice here is how long should this path be? And I'm saying, well, you should sample I and then do 2 to the I many steps. This will incur like a log factor. Okay, let me just finish with the third property I said I would talk about. The function is the property of is my function a K-junta or junta. This is this work introduced this property to property testing from Fisher, Kindler, Ron, Safra, and Samradnitsky. And here the definition of a junta is that you should think of the function as a computational device. And a function f is a K-junta if the way that you compute the function is by only looking at k of its coordinates. Okay? So this means that there's some hidden set S of size k such that the function value only depends on those bits in that subset S. Okay, so your function only depends on few of its variables. So for instance, well, this function, this dictator, it's a 1 junta because it only needs to look at one coordinate. On the other hand, the majority function, it's not a junta. In some sense, you need to look at all the coordinates before you can say, well, the majority of them are 0, the majority of them are 1. So there's been a lot of work on the question of testing K-juntas, of learning K-juntas. And in this model of querying the values, you can run a learning algorithm. And you can try to identify what are those K variables and then check consistency against those functions that only depend on those K variables. This will have a dependence roughly K log n. So you can identify those K variables, maybe run some binary search to get one of the variables and repeat. And then check consistency against those functions that only depend on those K variables. And maybe the main message of this original paper, as well as further improvements, is that you can actually get rid of this log n factor and test whether you're junta or not with complexity which is completely independent of the number of underlying bits. Okay, so this paper of Blay in 2010 pretty much nailed the question to get k log k plus k over epsilon. And maybe the important conceptual contribution here is that you can test whether you depend on k variables, even though you can't point to a single variable and say that's the variable that I depend on. Okay, if you wanted to point to variables, you would need some dependence on n, some log n factor from like basic information theory. Nevertheless, you can test whether this property holds without learning what those coordinates are. Now, there's been a lot of work on junta testing, and I wanted to highlight some of the recent work in also Artur mentioned slightly related models of property testing, and in particular of the tolerant testing of junta. So I could have changed the question. This comes with a different picture, where I can ask, is my function almost a junta? So it's the same definition as before. But now I require a relaxed guarantee on or a stronger guarantee on my property testing algorithm. So maybe, what do I want? I want an algorithm that here P is the property of being a junta. You really only depend on K variables. But you don't just want to accept functions that satisfy this very stringent guarantee. If it almost satisfies this guarantee in the sense that it's epsilon c close to only depending on K variables, then you should say, yeah, you're pretty close to depending on K variables. On the other hand, if you are epsilon f far from depending on K variables, then you should say reject. So in a way, this gives you a more finer control. But it turns out that these problems are also significantly harder. Not only do you have to accept K-juntas, you have to accept functions that are almost K-juntas. Intuitively, this means that even though if you see a violation, it could be the case that you're still very close, and the violation that you saw was actually quite rare. There's been a lot of recent work on tolerant junta testing. I think this started in a paper of Blake, Hanan, Eden, Levy, and Ron. And I mean, we still don't have like the full picture, but Shivam Nadampali and Shamal Patel, they have this like really beautiful paper where they give 2 to the square root k log this proximity parameter for non-adaptive tests. So these still has the property that there's completely independent of n. So you can't point to the various variables and say that you depend on these variables. And the dependence on k is better than exponential. It's 2 to the square root k. This turns out to be optimal for non-adaptive algorithms, for these fully parallel ones. But whether or not you can get any polynomial in k dependence for adaptive algorithms, that's also, I think, a wonderful open question.
Erik, so Blaze's result before, was that adaptive? The k log k plus?
It was, so I'm not entirely sure, but it was also for a slightly different definition of tolerant testing, and it had a bi-criteria component to it.
Okay.
Are you talking about the testing or the?
Well, I was talking about the testing.
No, for the testing, it is the adaptive from the previous slides. The k log k plus k over epsilon.
For this one.
That
This
one,
tester, this tester is adaptive.
That's adaptive.
Yeah. Good. Okay. And then finally, I also wanted to talk about another model of property testing where here you change the definition of the metric of epsilon farness. And if you're familiar with like pack learning, then this definition is going to be extremely natural. You want to test whether your function has the property, but the underlying way that you measure distance, what it means for a function to be epsilon far, is with respect to some unknown distribution, some unknown and arbitrary distribution. So you don't know, so okay, the distance between f and g is the probability that f and g disagree under some distribution that you don't know about. Before we were studying when this d was the uniform distribution. But the problem that you may be studying, it may be that there's another natural distribution that's the distribution that you care about. And even though you don't know the distribution, you have sample access to that distribution. Okay. And this line of work, this also, there were 2 recent papers on distribution-free junta testing, where perhaps surprisingly, you can almost, I think this, I forget exactly what the logarithmic factors are here. But essentially what you could do, even if you know the uniform distribution, you can get essentially the same complexity under a distribution-free model, even without knowing the distribution that you care about. But the guarantee that you get on epsilon is with respect to this unknown distribution. OK, that's all. So I'll let you guys go to lunch.
Do you have any questions? For the other problems that you mentioned, what's known about distribution-free versus
Which was
oh,
for monotonicity.
is there anything known about monotonicity in the distribution?
So I wasn't aware of one, but then this morning, Shivam and I were looking at, there was a exponential lower bound for monotonicity testing.
Oh, okay.
So correct. Yeah.
If your distribution was a product distribution, then you can essentially get results. Maybe not the root n, but you can get the other one. Actually, even the root n one.
So if it's a product distribution, you can get root n.
I think so.
Okay.
But we should check.
Any other questions?
I have a more high-level question. So this is more like when reading through all of these lower bounds, which of course you've worked on. It feels like we lack like good techniques to prove lower bounds, in the sense that if you read a lot of the lower bound proofs, they're like really long, but there's a lot of work that's just scaffolding and setting up notation and everything, and the kernel is usually hidden somewhere. Like, this is a very ill-posed question. Like, we have tools like Yow's Minimax Lemma, but that's pretty much the only generic tool that we have. Like, we don't seem to have any information theoretic tools to prove a lot of these lower bounds. Do you have any thoughts or? Yeah, sure.
So there's one cool tool which is just like offloading a lot to the communication complexity people.
You blame a lot.
Yeah, the blame.
BPM?
Yeah, like,
I was gonna ask
they
one more.
mentioned it. Yeah.
I'm not sure. I mean, it depends. The more you ask from the lower bound, if you want like a adaptive, uniform distribution, the easier seeming the algorithmic problem, the harder it's going to be. Yeah,
I mean,
not
if
a good
I-
answer, but
Because there are people who do streaming in the audience, right? I mean, in streaming, they have all these techniques with information complexity and this notion of a transcript and all of these techniques. And somehow in property testing, I don't think we've adopted them. Maybe we don't know how to use them. Seems there's an opportunity to maybe clean up a lot of the literature with using streaming lower bound techniques. But
yeah,
I don't know enough about it, yeah.
So that's a bit unfair, like this type of reductions, for instance, to communication complexity. It's like, you want to prove something is NP hard and instead you prove it's X hard or something. Communication complexity is much harder.
Right.
Model. So, like as Erik is saying, if you want to prove this problem right in front of you, usually you have to just get through that, like the mess or whatever it is. Like, I don't think there is this easy shortcuts of, even in a streaming when you mention, yes, you can reduce to communication complexity and you can prove it for something quote unquote simple. But if you want a nice result or like for problems which are algorithmically easier, then you have to.
I see. Do the grunt work.
It's the same with the algorithm. I mean, it's like, what is the key technique for the algorithms here? And all of them is.
another question. Okay.
Anyone else? Well, thank you very much. Okay, so